Go.
Good morning, ladies and gentlemen. We are going to do our changes lab today. The purpose here is to observe and measure the properties of simple circuits.
Simple circuit.
Okay, so our materials, we have two batteries here. We have an oblong bulb,
Yep.
and we have a round bulb. We don't really know what oblong means, but it's not round. So.
Well, yeah, you got a round one and an oblong one, and that one's not wrong. That must be the oblong one.
Yeah. Okay, so using one cell and a light bulb, we're going to start with the round one, so I'll put this one over here. We are going to measure the current in the circuit, and then we're going to measure the potential difference, and then potential difference, and then it looks like we're going to calculate the power.
Yep.
Okay. All right, so let's go ahead and set this up. So I am going to connect this guy
One side of the bulb.
to here, yeah. Oh, there we go. I was like, where's my thing? Here it is. And this side, right there. So now here is our lovely
Let's see if the bulb
circuit
lights.
right there. Okay. And oh, okay,
It
there you go.
lights.
It's dim, but it lights. Okay. And what does our reading on there say? Can you see it?
I'm gonna call that 170 milliamps.
170 milliamps. So, are we gonna call it 0.170 amps then? Or
That's a good idea.
Okay,
Convert it into amperes.
170 amps. And then, oh, and we forgot to put an R. We forgot to put this guy in.
So put the red one on this side.
Yeah, but it goes over there.
You know, this is a voltmeter, and it's measuring the electrical potential difference from one side of the bulb to the other. Bulb comes on, and hold still there. I'm going to call it 1.3 volts.
Sorry, I'm struggling. Okay, 1.3 volts.
One of the problems is it's hard to have a good contact with the
Yeah.
battery.
So, do we want to wait till the very end to calculate the power?
Well, that's just current times voltage.
Yeah.
That's just IV. They don't have to do it. No, that's their job, not
let them do
ours.
it. Okay. All right, so you go ahead and calculate PIV, right? Power, current times voltage. Okay, so now using two cells, light the bulb, again, measure the current and the potential difference. Okay, so we're gonna stick these two bad boys together. And bada boom, bada bang. Ooh, look at that.
It's brighter. And let's call that 250 milliamps and 2.6 volts.
Okay, so 250 and 2.6.
Yep. So that's trial 2. And you guys are writing this down on yours, yes?
And you know, as we go, you can either pause it and calculate the power now, or once we're done. Okay. Oh, question. Question for you guys: what difference did you observe between trial 1 and trial 2?
Oh, there's something about the brightness of the bulb. And then there is the measurements.
Okay. All right. Oh, look at that. Okay. All right. Okay. So trial 3, the oblong bulb. So here we go. Let's switch this guy out. We're gonna put this guy in here. Get that on there.
There you go.
There we go. I'm like, how do I keep it on there? Okay. All right. So using one cell, measure the same things. Here we go. Okay. Am I touching that side over there?
Boy, that's weak. That's not very
know.
bright at all. Okay, and what we're getting here is, I'm going to call that 60 milliamps.
Okay. And then what about the voltage?
Oh, that's a good question. And that's about 1.3 volts.
Okay. So 1.3 volts. And you said 60 milliamps. That's
60
gonna be
milliamps. That's weak.
060 amps. Right. 1, 2, 3. Yep. Okay. I got that. So I've got looking like this.
So that's what you guys written down in yours, yes?
Mm-hmm.
Okay,
Yes,
what
that's
is,
right.
there's a question
Yeah.
there.
What was the same and what was different between trials 1 and 3? Okay.
Well, there was something about how bright the bulb was. And then there was something about the measurements.
Okay.
So those are what you should take a look at.
Okay, lastly, same idea, but we're gonna put two batteries in there. Okay. Ooh.
Oh, it's brighter.
Oops.
and that's about 93 milliamps and about 2.8 volts.
Okay, 93 milliamps. And what was it? 2.3?
2.8 volts.
2.8 volts. Okay,
And then there's a question.
and there's a question. What was the same and what was the difference between trials 2 and trial 4?
Yeah, you only got two things you can look at, and that is what the bulb was doing and what the meters were doing.
Okay, so think about the answers to those questions, write your answers down. And the next thing you're going to do is you are going to transfer your data from the other side to this side. So write down what your current was, what the electrical potential difference was. Write down whatever you calculate your power to be over here. Do they need to show their work here, or can they just write their answer?
Showing your work is always a good thing.
And then I want you to calculate the ratio of the electrical potential difference divided by the current.
So make a fraction with the potential difference on the top, the current on the bottom, and then put that in your calculator and put the answer.
Yeah, and it says the units are volts over ammeters for now.
Yeah.
Okay. And then let's see. So once you've done that part, the next thing you're going to do is use the correct symbols, make a diagram showing a bulb, the cells, the ammeter, the voltmeter connected properly in this circuit. Now this one, so we're going to use 2 batteries, right?
It doesn't matter.
Okay.
It was just, the whole point is being able to use the correct symbols and showing how the ammeter is hooked up and how the voltmeter is hooked up. That's a basic fundamental difference. And so we're going to stop right here and then we'll pick it up later.
All right, ladies and gentlemen, here is what your diagram should look like. I'm going to go ahead and do the one with 2 batteries, so it'll look like this.
Yep.
Okay, and then let's see, we had the light over there, ammeter over here, okay, and then we had the voltmeter attached here, right?
And it's really important. In order to measure current, the ammeter has to be in the circuit, in the flow. So the electrons come out, they go through the bulb, they go through the ammeter, and then they come back to the batteries.
Yeah, it can't be over here or something.
And the voltmeter measures electrical potential difference, so it goes from one side of the bulb. There's a difference in the energy of the electron from one side of the bulb to the other. That's what the voltmeter is measuring.
Important. Okay. All right, so that's what you should have. Let's rock and roll with
Let's just practice some stuff.
Yeah,
here.
with some questions here. A car battery causes a current of 2 amps through a lamp while 12 volts is across it. What is the power used by the lamp?
What was that equation for power? Let's see. I think it's on the next slide. It could probably.
Right there? Ah, there it is. Okay. Power is the rate at which energy is converted. So it could be energy over time, okay, for watts,
Yeah.
right?
Yeah.
So let's go back to this question over here. So let's see what we
Oh,
have.
you know what?
I think it's the wrong equation, right?
We don't have time,
Yeah, instead
and we don't have energy. We have, but what
We
was
have-
what was
we
that
have a-
equation? It was
we have
PIV, wasn't it?
PIV, right? As I read that, I was like, that's our other definition
Sorry,
of power.
Mr. Boykin blew it.
That's the one as we go up the bleachers, right?
That's right.
Okay, so our current, if we want to figure out what power is, our current here is 2 amps, right?
2 amps.
Okay, times our volts are 12 volts. So 2 times, that's going to be 24, right?
24.
Okay, and amp meter times a volt.
Amp
talked
times
about
volts,
that?
which is a, let's see, an amp is a coulomb per second.
Coulomb per
Second.
second.
And a volt is a joule per coulomb.
It's a joule per coulomb. These cancels, a joule per second. That is a
What?
what?
That's right.
Okay.
All right, now let's go to the next slides because I blew it. So we've got 24 watts, and power is the rate at which energy is converted. So what is energy, what kind of energy do we have, and what is it converted to? We've got electrical energy.
And it's converted to probably heat and light energy.
Heat and light, that's exactly right. So you got electrical energy is converted into heat and light. And have you ever unscrewed a light bulb after it's been on for a while? Sucker's hot.
Yeah, my mom's always like, let the light cool, turn off the power. Mom's always freaking out. Okay. So, because my dad he does everything by hand.
Yeah.
Okay. And himself. The current through a light bulb connected across the terminals of a 120 volt outlet is 0.50 amps. At what rate does the bulb convert electric energy to light?
What are they talking about here? What are they asking us for?
Well, it sounds like when they talk about the rate of turning something to light, is that still? Oh, I'm going the wrong way here. Is that still just PIV?
Well, power is the rate at which current energy is converted from one form to another.
Yeah.
And
So
we
we're just trying
have
to find the power, right?
yeah. So we have
Okay.
to find the power. By the way, a 120 volt outlet. That is a 120 volt outlet.
Yeah. Isn't that like the standard?
Yep, that's a
Okay.
standard, same as you got in your house.
Okay. So this looks like it's gonna be pretty easy. So just multiply that times 120
Half of 120
volts is 60
watts.
watts.
See how simple this stuff is, boys and girls?
Yeah. Okay. So,
Just a little practice.
yeah, easy. What did the ammeter do when you turned the battery around? And then why? Okay, so here's our ammeter. Okay, we'll just go ahead and go with one here. Okay, so this is the normal way it was,
Yeah.
right? And as I turn it around, ooh, it goes the other way.
So the needle goes either up or down. Why is it doing that?
What's going on? Well, in flipping the battery, essentially what's happening is, are we actually flipping the current here?
You are, because remember, electrons are repelled from the negative and they're attracted to the positive. So in that way, they're going this way around the loop. And when you connect it, and now they're going this way around the loop. And so the ammeter is not only giving you magnitude, but also direction. We talked about that yesterday when you said, wouldn't it be nice to have the zero in the middle?
In the
and
middle,
you-
right?
yeah.
Okay. All right, so that is the why for that.
Yep.
Okay. Show which direction electrons are flowing in your circuit diagram.
So you got that on your lab.
Okay.
And which
so
side is positive, which side is negative?
negative, positive side. Don't forget the positive side is the one that is at the length, the one that
Two
is
fingers.
long enough to take 2 fingers, and that one's just one. And we know that electrons are flowing this way, out of the negative, whoosh, and into the positive. Sweet. Okay. What else do we got here? Why did the voltmeter needle go one way or another depending on how you placed the wires?
Now, we haven't talked about this yet, and let's look at the voltmeter.
So we'll keep it like this. So I'm gonna go ahead and let's go this way first, or let me flip this way. Okay, so here's the normal, the quote normal way, right?
Okay, we're measuring a little under 1.5 volts.
And if I flip the battery,
You
or
turn the
if
battery
I-
around.
Yeah, or if I flip sides, either way, same idea. Okay, again we have it going that opposite direction.
All right, so this is different from an ammeter. Voltmeter is measuring something different. What the heck's going on?
So it's measuring the electrical potential difference, right?
What does the word difference mean?
Change,
Yeah.
right?
And what you're measuring is you've got the one wire here, one here, so it's measuring the difference in electrical potential energy from one side of the bulb to the other side. And what's happening to the energy as it goes through the bulb?
Well, it's getting less, right?
It's
decreasing.
converted into heat and light. That's
Yeah.
absolutely right.
Yeah, so it's decreasing, but why? Because it's being converted to energy and to heat and to light.
Yeah.
Okay.
And so this is expecting things to go from less to more. From more
to
energy to less energy. All right, when you turn the things around, it's seeing more energy, less energy to more energy.
Which reminds me, so Mr. Boykin had a really great explanation for this. So if we've got our
You can do it right here.
Yeah, we've got our bowling ball. You know, when we talk about the gravitational potential energy, if I'm picking the ball up,
The potential energy is increasing.
and as I put it down,
It's decreasing.
Okay.
Okay, now do it again. But now, wait a minute, do that again. You did it too fast. Okay, now everything's upside down. Now it looks like the energy is decreasing.
Yeah.
And that's just like changing the wires on the
It's all about
voltmeter.
it's just about the lens at which basically that
That's a great way to put it.
Voltmeter is reading it. Okay. So hopefully that makes sense. Okay, let's rock and roll. I think we're good there. Why is each bulb brighter when you put a second battery in the circuit?
Well, what did you notice about the numbers you wrote down?
Well, we noticed that when we put a second battery in the circuit, that was this one and this one, right?
Yeah.
So from here to here, our current increased.
So more current, what else changed?
It got brighter.
It got brighter, but also your potential difference increased.
Pretty much, it kind of doubled here, right?
So not only did the current go up, but the voltage went up.
And it got brighter.
Yeah.
Okay. So why is each bulb brighter when you put a second battery in the circuit? Well, you've got more current in there, and more current will make it essentially. There's more electrons flowing in there, more energy. Okay, more
Yeah.
power.
Yeah. And what is power? That's energy being converted from one form to another. So you got more electrical current, more potential difference, and you're going to have more power. That is a brighter light, a greater
Yes.
conversion from.
More.
That's right.
Sweet. Miss Moore. Okay. All right. So, what is the relationship between how bright the bulb is and how much current flows through it? Did we just do
I think
this
we
one?
just talked about
Okay,
it.
did I go to the? Why is each bulb? Oh, okay. Okay. What is the relationship between how bright the bulb is and how much current flows through it? Well, more brighter is more current,
That's right.
right? So that we just talked about more brighter, more current.
Yep.
Okay, for the same number of batteries, why did one bulb have more current than the other?
Now this is a big question, and the answer is it must be something different about the two bulbs. And it's not just the glass in the bulbs. Everything was the same except the little wires on the inside that heat up.
Yeah.
Those little wires that heat up.
So it's almost like it was harder for the electrons to travel through this one than it was for this one, right?
It was easier. You got more current. It must be easier to flow through. And less current, it must be harder to flow through.
Okay, so let's go ahead and take a look at my next slide here. Resistance. I think this is the word we're looking for.
Yep.
Resistance of a material is how hard it is for current to flow through it.
This is today's big idea, boys and girls.
So it was the oblong bulb that was less bright, right?
Yep.
So that one must have had more resistance.
Because it had less current flowing through
Because
it.
it had less current flowing through it.
Yep.
Okay. Okay. So anything else to add there?
No, I think that's good. We
It's
can go
simple,
right
but-
on to.
Okay. So.
Oh no, you went too far.
Oh, there we go. Sorry. So here is Ohm's law, resistance for R, and it is a ratio of the electrical potential difference over the current.
That's
or
right. And
verb.
Ohm's law rules all electrical phenomena. This is the big idea that we're going to encounter. There are lots of other ideas, but this is the big idea. There are three variables here in our little circuit. We've got current, we've got potential difference, and we have resistance.
Cool.
And here's our definition of resistance. It's how much voltage is required to kick 1 amp of current. If for the same amount of current you need more voltage to kick it through, that's a higher resistance. If it takes less voltage to kick the same amount of current through, then it has less resistance.
And our units for this are going to be an ohm. So a volt over an ampere is an ohm, and that is our symbol for it.
That's the Greek letter omega.
Okay. Oh, and then that's where we're
You
going
know,
to stop today.
let's stop right here.
Yeah.
And
Oh, so finish up your lab if you haven't finished it yet. And that's all we've got for today.
oh, one last thing that occurs to me. We had you calculate the ratio of the potential difference to the current. What is that?
What do we call that? Ooh, maybe I'll make that a little.
I think it's this right here.
Resistance.
That's right.